Okay, good morning everybody. My name is Florian Wolf. I'm a PhD candidate at the Technical University of Ilmenau, and I'm also in the industrial PhD program at SAP HANA. And my talk today is about the calculation of optimality ranges for relational query execution plans. So what are optimality ranges? Well, let's consider this example query. It's a very simple chain query joining 5 relations having estimated cardinalities and selectivities as depicted here. And what query optimization usually does is it enumerates some plans. Of course, the plan space is much larger than shown here. And then there's a cost model that assigns cost to every single plan. And eventually the plan with the smallest cost, the cheapest plan, is selected to be the optimal plan. So let us now consider a plan caching scenario where this query is executed multiple times and the execution plan is cached for future executions. And let us also consider that this is an H-tab scenario, such as the ones that SAP HANA supports. So the probability is pretty high that a few changes in the database won't make this plan suboptimal, but at some point it will be suboptimal. So the question is, how can we detect that pretty easily? Well, the answer are optimality ranges. They can be annotated on every single edge in the query execution plan, having a lower and upper bound for the cardinality. So for this given example here, the optimality ranges would look like this. And in the talk I will basically explain for this example how the algorithm works. So the agenda is we start with the calculation algorithm, then see some experimental results. I will discuss some applications for the ranges and finally conclude the talk. So let's come to the calculation algorithm. That's the main contribution of our work. And the first building block is cost intersection of query execution plans. That had been done before, but I will explain how it works because it's a fundamental building block. So here we have our optimal plan, and we calculate the optimality ranges only for optimal plans. As I've said, it has the static cost for the cout cost function. And now we assume we want to calculate the optimality range on this edge, on the RS edge, meaning the join result of joining R and S. So what we can do is we can model the cost of this plan as a function of this cardinality on this edge. So for the cout cost function, it gives us a nice linear function. We call this kind of functions parametric cost functions, and we can plot them here. So we have on the x-axis the cardinalities and on the y-axis the costs of our entire plan depending on RS, and we see it's a nice linear function. We of course support other cost functions that are not linear, but just as an example. And then we basically compare our optimal plan with an alternative plan that had larger static cost, so it was not picked as optimal plan. And we can also model the costs of this plan as a PCF on this cardinality. And we can also plot it in this figure here. And what we now see is that our optimal plan becomes suboptimal at this point, because at this point the alternative plan has smaller cost. So that gives us a first bound for the optimality range. The question now is, which plans do we have to compare with our optimal plan? And that brings us to the next slide. So I will spend some time explaining what you see here. It's essentially a simplified dynamic programming plan space for our chain query. And dynamic programming is based on Bellman's principle of optimality, saying that an optimal solution can always be constructed from optimal sub-solutions. So we see here basically some plan classes, for instance, the plan class RST, which is the result of joining RS and T, and that can be constructed by either joining R with ST or joining RS with T. Both subplans have costs, and only one of them is the cheapest. Of course, there can also be multiple cheapest plans, but let's assume one of the cheapest plans is then selected as optimal plan for this plan class, and that candidate is then used to create new candidates for higher plan classes. And basically the optimal plan is always depicted in bold font, and the optimal plan, the final plan class, is the plan that we execute. So for example, we also see now here in blue the optimal plan, and like the example was to calculate the optimality range on this RS edge. So what we now see here highlighted are basically all the plans that costs can change when the cardinality of RS changes. So this can mean that in these plan classes, the decision of the optimal plan can change when the cardinality of RS changes. So in order to now calculate the optimality range, I said we have to compare the optimal plan with alternatives, but we can already start doing that on a sub-level plan. So we basically follow the path from RS to the final plan class, and on this path we compare parts of the optimal plan or the optimal plan with its alternatives. So the initial optimality range is 0 to infinity, and now with comparisons we try to narrow this optimality range. The first comparison is in the RST plan class, where RS, T is the optimal plan, compared with R, ST, which is independent of RS and has static cost. Consequently, we get a new intersection point, and this is an upper bound for our optimality range, so we can further narrow that. The next interesting plan comparisons are then in the final plan class, so where RST, UV is the optimal plan, and we start comparing that with the first alternative, which is this plan. We get a new intersection point that's within our current optimality range, so we can narrow the optimality range. The next comparison is this plan. Well, here's the intersection point is out of the current optimality range, so we cannot further narrow the optimality range. And then the final comparison comes from this plan alternative. And as you see, this is RSTU joined with V, and RSTU is also depending on RS. So for this alternative, we get multiple plans that we have to compare. So it's in sum it's for 1, 2, and for this one 3, 4. So we have 4 plans for this alternative to compare with the optimal plan, and one of them intersects within our current optimality range, so we get a new lower bound, and that's the final optimality range that we've seen in the initial example. And the example I've just given, that we get here like 4 plans, that can be a much larger number, and we also have a pruning strategy described in the paper, how we can keep the number of plans that we have to compare here very low. Details in the paper. So for this algorithm, or for the example that I've just shown, we made some assumptions that can be relaxed. So first of all, we consider the linear cost functions. Well, if the cost functions are linear or not, this depends only on, or that only affects the cost intersection, and it has been shown before that that also the cost can also be intersected for nonlinear PCFs. We also considered just join queries. There's also no limitation. We can support any kind of operator, because each operator has an estimated output cardinality, and that is most probably part of the cost of the plan. We consider dynamic programming enumeration. In the end, it doesn't really matter how we enumerate the plans that we compare with our optimal plan. We can also use transformation-based and other strategies. We just pick dynamic programming because it seems to be, or we argue that it's the most efficient way to calculate the optimality ranges. Another assumption was that we basically, or let's say we, that's not an assumption, it's more or less, I mean the point is we only support optimality ranges for enumeration optimization strategies that guarantee to find an optimal plan. So we do not support randomized algorithms, because the decision of the optimality range and optimizer should be consistent. So when the optimization enumerates a different plan space, then we would enumerate for the range calculation, then it would be questionable what the optimality range would say. So that's why we're limited to, or we restrict that to algorithms that guarantee to find the optimal plan for the given inputs. Also, we consider only to have only one optimal plan per plan class, but of course real queue optimizers, they can have multiple optimal plans per plan class, having additional physical properties such as sorted columns. We also explain in the paper how that can be supported, and we assumed in the example that there are no estimation errors in parallel subtrees, so in bushy trees basically. We explain in the paper that this requires to introduce additional variables. And we explain, first of all, how this number of additional variables can be reduced or kept to a minimum. And also, it does not really affect the way how we compare or let's say the number of plans that we enumerate and compare. It only affects how we intersect the cost. So that was the calculation algorithm. So the question is, how do optimality ranges look in reality? Before we start with the first slide, which shows how optimality ranges look for a TBCH-like benchmark, I would like to explain the state-of-the-art approach, which was we take the estimate for an edge and add a certain percentage to the top and to the bottom of the estimate, and that was the optimality range. and we will see that this does not hold really. So we have here TPC-H-like queries 8, 9, and 10. TPC-H-like because it's just a pure join queries. We have the different edges of the query execution plan on the x-axis and the cardinalities on the y-axis. And we basically see the optimality ranges having the lower bound, the upper bound, and the estimate in the middle. And what we see here is that first of all, the width of the optimality range is varying. So we have very narrow optimality ranges and very wide optimality ranges. Also, what's interesting is the position of the estimate in the optimality range. So we can have optimality ranges pretty close to the lower bound or pretty close to the upper bound. That means that already a small change in the cardinality can lead to a better plan, or it can also be the case that the cardinalities can change a lot and we don't get a better plan. So the baseline from that is that, or the bottom line is that the simple heuristics fail to characterize the optimality ranges precisely. We also did some experimental analysis on the complexity or on the effort to calculate that. So we have here the query size, the number of tables on the x-axis, and the number of enumerated plans on the y-axis. We show basically optimality range calculation as box plots, and we also show dynamic programming optimization as kind of a baseline. So it's a different problem, but we just want to show how much dynamic programming would enumerate. So the optimality, or calculating an optimality range, basically depends on the level of the edge in the plan, on the tree structure, and how efficient the pruning was. We see that the median is below what dynamic programming does, but the worst case can be larger than that. We also did time experiments. Just the message here is that it correlates with the number of enumerated plans, and details can be found in the paper. A very nice last experiment I want to show is on the pruning performance of our algorithm. So we again have the query size on the x-axis and the enumerated plans on the y-axis, and we compare like pruning enabled and disabled for the chain queries and for star queries. We see that for 20 tables, without, it's logarithmic scale, so without pruning is over 220 million enumerated plans, and with pruning it's just around 5,000. So pruning really makes this algorithm applicable. And for the star query, we stopped at 13 tables, where without pruning we are over 1 billion enumerated plans, and with pruning it's just 60,000. Okay, if I have a bit more time, I can also talk a bit about applications for optimality ranges. So in the introduction, we've seen the plan caching scenario. Another application would be parametric queries. So there's one pretty good approach for parametric queries, which is called progressive parametric query optimization, which basically for each parameter that arrives, searches the optimal plan and then caches the plan. And when new parameters arrive, it checks if there was already a plan that was close in the selectivity. And the question is, what is close here? So I think, or we argue that optimality ranges can improve this approach to have a much more precise plan choice. Also in mid-query optimization, it's a pretty important topic to know when a plan becomes optimal and when to switch to a better plan. And also plan robustness analysis can be an application for that. So as I've said, the position of the estimate in the optimality range gives us a lot of information. So if I have a very wide optimality range and an estimate in the middle of this range, then I know that the cardinalities can change a lot, and the plan will stay optimal. Okay, so conclusion, well, as I've said, the simple heuristics fail to characterize optimality ranges precisely. We presented this algorithm to calculate exact optimality ranges by taking all necessary plan alternatives into account. We also have this pruning strategy, which is a large contribution of our work, which significantly reduces the number of enumerated plans. And we've seen that optimality ranges can be a generic and important building block in query processing. So thank you so much. I also have a poster today, and we also have a poster tomorrow because we participated in the programming contest. And I would also like to invite you to our talk at VLDB this year. So we have a paper on robustness metrics for execution plans in Rio in August. Thank you.
trying to go to the mic. I understand the room is pretty wide, so we'll try to also take questions from other parts.
Hi, thanks for the presentation. So in the presentation, you talk about how to calculate this optimality range based on cardinality, right? But in query optimization, the cost of query not only dependent on cardinality, but also dependent on the distribution of the data, or histograms. So I'm wondering, have you considered that aspect of the optimality range, and why you did not include that?
I mean, like, distribution was the question, or?
Distribution of the data, or histogram.
Yeah, so basically that affects the cardinality estimates, and
yes.
that's like considered in the cardinality estimation, basically.
Oh, so you, okay, so
and
consider.
we just work on the estimated cardinalities then. So,
I
and
see.
we just have the same information as the optimizer has. And the question is like, what would the optimizer do? Right?
Okay, sure.
So I think I probably didn't understand something you said, so it's a clarifying question, which is, if you give me a plan and say under which condition, what are the ranges for which this plan is optimal, that's a kind of a hard problem, because it's hard to know the ranges for which this will be optimal. And how do you solve that problem? And that takes a bit of time, because...
So, I mean, that's the algorithm I explained.
Do you have a proof that it actually is? Do you have a proof of this, that
We
this
have
algorithm is correct?
We have experimental proof. So
do you have a correctness proof of this?
No,
Under the assumptions of that you have histograms. At any point in time, the stat is going to be recompiled, right? And that is going to trigger
so we
the
don't
change.
have a proof in the paper. We just verified.
Have you compared with Volker's technique? Volker and others had a paper on this topic, which is on optimality range. There is prior work in this area.
Maybe we can
Okay.
use offline.
Did you consider how query transformations affect your approach?
Sorry,
If you have a complex query where we have subqueries, that you have a nest, and
yeah. So, like I said, we also support bushy trees, and we basically, if we have parallel subtrees, we have to model their cardinalities as additional variables in the parametric cost function, and that affects the cost intersection that I explained. If that was your question.
so in practice, it doesn't matter whether a plan is optimal if it's within, like, if it's within 10% of the optimal, then it's probably good enough. So would this approach generalize to finding plans which are within a particular factor of the optimal plan?
So, I mean, what systems usually do is they try to find the cheapest plan, right? And we are building up on that, figuring out when would the system or the optimizer select a different plan.
Yeah, but let's suppose I thought the data, the cardinality was going to be 1 million, and it turns out to be 1,200,000. If I use the same plan, I may not be optimal anymore, but I might be only 1% worse than the optimal at that level.
Yeah.
So would this algorithm tell me that I'm still okay, I don't need to replan?
So, I mean, the algorithm will search a new plan in the end, or will trigger a new plan search, but it can be also the other way around, right? You can also be like a few tuples off on a very low level edge, and then in the end you have a significantly different plan choice in the end.